The universe is a big place, like really big. So big, in fact, that it is demonstrably infinite in size. This statement has been of some academic interest to me in the past, so I thought I'd talk about it today. So my full thesis is called Investigating the Arc-Minute Microkelvin Images Sunyaev-Zeldovich Selection Function of Galaxy Clusters. It sounds, shall we say, a little convoluted, but let's break it down a little so it actually begins to make some sense. So if you take, let's say, a star, for example, like our Sun. To us on Earth, the Sun is rather important, but on the grand scheme of things in the universe, it is a very average and unremarkable G2V type star. Now, if you were to take many stars and place them on the night sky, you could maybe call them a constellation. If I'm honest, so many people have asked me what it feels like to be an astrologist, and although astrologian makes a cool class in Final Fantasy XIV, unfortunately, astrophysicists don't really count stars in the real world. But on the other hand, if you were to count a lot of stars, say not 4 or 5 of them, but rather 200 billion, you end up with what we'd call a galaxy. Now inside that light halo you see in the center is a supermassive black hole the size of about 4 million suns, so quite big all in all. Unsurprisingly, not every galaxy is the same as they come in all shapes and sizes. Now, if one were to take many of these galaxies together, say 10 of them or so, you'd get something called a galaxy group. We live in such a group, imaginatively named the local group, because, well, we're in it, inside, I guess, like locally. So here we are, the entire human race on this tiny blue speck in the vast emptiness of space. The Milky Way, along with Andromeda, are actually the 2 largest galaxies in this local group of ours. Interesting fact, by the way, we are actually on a collision course with Andromeda, and in about 4.5 billion years, it's about to get real dicey around here. It doesn't end quite there. If we went a little bigger and added more groups of galaxies to the mix, we end up with our local supercluster, which is called the Virgo supercluster. Typically, it takes about 100 to 1,000 galaxies, give or take, before you get to a galaxy cluster. That's quite big. Okay, that took a while, but finally we have arrived at the galaxy cluster in the thesis title, which is what I spent most of my time studying during my PhD. Now, clusters of galaxies are quite big. Specifically about 10 to the 14 to 10 to the 15 solar masses, or about 1 quadrillion suns. That's this many of our suns combined. Keep in mind, about 85% of the matter is actually dark matter that we can't see, but we'll discuss that another time. So even though galaxy clusters are literally massive, we still have a lot of trouble detecting them with our telescopes on Earth. The main problem is that even though they're very large, they're also unfortunately very, very far away. So far, in fact, when we use our telescope in Cambridge to observe them, they appear only a few pixels in size. The telescope I used is called AMY, short for the Arc-Minute Microkelvin Imager, which is sensitive to the radio spectrum of light. Now, radio waves have a major advantage in that they pass through the Earth's atmosphere very easily, so we don't need to borrow Elon Musk's rockets to send our telescopes to space. That's why with the Hubble Space Telescope, or more recently the James Webb, you needed a rocket, a very big one, to launch them because our atmosphere, while great for keeping us alive, is a major detriment to most of the astronomy that we do. Now, there's something called the selection function, which is a consequence of making any sort of observation in astronomy, and we have to try and understand this for the sake of this video, unfortunately. Let's do a thought experiment. Let's say I'm an astronomer, and I look at the night sky and I only see 20 stars. Would it be correct to assume, then, that given this is what I see, there must obviously be only 20 stars in the known universe? The answer is of course no. One would think it would be silly to fall into this sort of very basic fallacy, but you would be surprised at the number of physicists who are way too overconfident in their equipment, their telescope, and their data. So given all of this, how can one know that the universe has certain intrinsic properties and it's not just your instrument's inherent limitation? This is, I guess, what you would call the selection function. Unfortunately though, calculating the selection function is not something astronomers like to do because it's acknowledging your instrument has a limitation, which is not good for funding. If the James Webb admitted all of the limitations of their telescope, getting that $10 billion worth of funding may have been a little more difficult. Look, $10 billion equates to a lot of peas, one must admit. Think about all the fish and chips that could buy. Okay, one final thing before we get to understand my work and what I actually did. This part can be a little bit confusing, so I'll try and explain it in a way that makes sense. In the very early universe, a long time ago, there was the Big Bang. This explosion was so big that it created something called the cosmic microwave background, which is radiated evenly across the known universe. This radiation moves through space-time randomly and have a low chance of interacting with particles inside of galaxy clusters. And when the interaction actually happens, we can observe it with Amy. Now this phenomenon is the so-called Sunyaev-Zeldovich effect. And with that out of the way, we can finally translate my thesis into something which is a little easier to understand. In plain English, my work was on studying our telescope's limitations by using light from the early universe. So I hear you ask, why didn't you just call it that then? Well, it would have sounded less impressive, obviously. Okay, jokes aside, it actually seemed all rather straightforward. Well, just figure out the errors of your observations and perhaps we arrive at some kind of answer. The complexity in the work that I did wasn't so much in the hypothesis. For the most part, you're able to ask any question you want. Are unicorns real? Does God exist? And why in my League games do people keep feeding? Those questions are fine, but the reality is to prove something quantifiably is difficult. And even if you could prove it, will people believe you or even care to read what you've done? Answer, no they don't, because see our fine mess with COVID-19. Our observations with Amy, and to be honest, most experiments while doing just anything in physics, yields some form of probability curve if you're using Bayes' theorem, and it looks something like this. Now we're asking the original question again. How do you know that your data is accurately represented here? The true answer is that we don't really know as much as we think we do. And unfortunately, to figure this out, it's really complicated because 1, the data is n-dimensional. 2, writing the code to test this takes quite a long time. I used Python and MATLAB. That's not very relevant. It doesn't really matter too much. And 3, there aren't any existing mathematical formulations that is designed to tackle this problem properly. So I had to invent my own solution. Most of what I did for our little measurement problem required a simulation of clusters of galaxies. Simulations in physics are very important because it allows you to pretend as if something happened without actually doing it. For example, simulating a car crash has the huge advantage of not needing you to be in the actual car crash. And then, after some few thousand or million simulated car crashes later, Tesla does a real crash test on their Roadster to see if it is as safe as what their simulations believe. This is done everywhere, from fighter jets to, say, simulating whether or not someone will pay their mortgage back on time. This, unfortunately, also requires a lot of CPU and GPU power based on what you're doing. This is another reason why we are short on graphics cards, because beyond crypto mining, we used a supercomputer called Darwin to simulate some millions of clusters of galaxies, so I didn't have to observe them. Observing them in the real world just isn't feasible. So in the end, over a lot of simulations, I found that we had some biases in our techniques, which I fixed. I also applied the same method I developed to test the accuracy predictions of N-body simulations generated by other research groups. It's not very good to test your own method on your own data because, well, it's like trying to prove that you're good at playing chess by playing chess with yourself. So to avoid the trap of playing chess with myself, I did a lot of external testing. Fortunately, it worked, but not quite as well as on our own data, which wasn't too surprising to me. But I guess this all turned out quite well in the end because I found the approximation to the Amy selection function. So if I could summarize what I learned throughout my PhD, it would be something like this. Physics is really hard. So that's it. I mean, my thesis in a nutshell. There's no way anyone in the known universe is still watching this video at this point. So here's my favorite league champion. Press Q to get stronger.